Testing, testing. Bing bong, bing bong. Boys, colleagues, fellow homunculi, part-time gardeners, and computer touchers. This is 266 Palindrome Permutation. Doing this in TypeScript. I feel like, it's JavaScript, but with the static type checking and stuff, you guys are going to see the types I'm using, so it's actually easier to follow. Pog. So, given a string, determine if a permutation of the string could form a palindrome. So here we're given the input code, and we see that this is false. We're given AAB, and they return true. Well, you look in your head, and you're like, AAB is not the same forward as it is backwards. AAB backwards is BAA. But there is a permutation of AAB, which means the order is different. So ABA, which is actually going to be a palindrome. So that's kind of the trick here, right? So with a palindrome, right, you can traditionally do like the whole, reversal algorithm. So like let start is equal to 0, end is equal to the length of the string minus 1. Then you can check as you're going, iterating towards the center, right? And if those characters are ever not the same, right, then you don't have a palindrome. But you can't do this way, right? So how do you do this? So on first thought, one might think, well, I know how to check if a string is a palindrome. Why not generate all possible permutations of the string and just check if it's a palindrome on that? Well, that's going to require a lot of space, especially as your input size increases. And it's just not a fast way to do it. Also, it's a very difficult way to generate all the palindromes, generate all permutations. You don't have to, right? So when you have a question like this, it's easier to just kind of, if you take the question too literally, right, it's a little bit tougher to figure out the answer. But if you just look at the input and try to figure out what's the pattern here, right, then you can kind of start to see, and I have some stuff written here. We're just going to work through it. So we're going to try and figure out, the base properties that kind of make something a palindrome, right? Because we have to look at all permutations. So there must be some structural indicators, right, for a string that you can kind of instantly tell whether or not it could be rearranged to be a palindrome, not that its current form is or is not a palindrome, right? So how do we do that? So what information do we have about a string? Well, we only have the string, right, the letters in a string, and how many times they are shown. So working with that information, what can we kind of deduce, right? So here we have AAAA, which is just 6 A's, right? And so I've written here on the side, right? I don't know why I have A equals 5 here, but we can see that we have AAA, which is 5 A's, right? And this is the palindrome, forwards as it is backwards. And if you rearrange it, that's why either way doesn't matter. Any way you put these A's in, right, it's going to be a palindrome. All right, but then you have AABB. Now this is a palindrome, right? Strictly speaking, this formation of this string is not a palindrome, but it can be rearranged to make a palindrome. What does that palindrome look like? You would have A, you would have B, or one version of it could look like this, right? BAB, right? Because you have 3 A's and 2 B's. So what are the properties here? So we notice that in this first problem, right, if A is equal to 5, we have 5 A's, right? Or if A is equal to 6, we have 6 A's, right? Either way, it's still a palindrome, right? And we see here, right, that A is equal, we have 3 occurrences of A and 2 occurrences of B. So we have A has, so we have an odd occurrence of A, right, and an even occurrence of B. Well, we know, right, that it doesn't really matter if this is 2, 4, 6, 8, 10, 42, 368, 180, right? What all that really matters, right, is that the the number is even, right? So we know that if a number is even, it doesn't really matter how large a number is. We can always split it in half, right? One half of the string will go on the left half, and one half of the string will go on the right half, and it'll be a palindrome, right? But we notice, interestingly enough, right, if we go back to just B being 2, right, so we have an even occurrence here, and we can have an infinite number of even occurrences, right? So we can have C equals 4 and D equals 6, right? And why is that, right? Because if you take a look, right, if the number is always even, you can always just split it in half and place one number on the right-hand side. And so we don't need one letter on left and right-hand side. So we don't even have to actually write those letters to occurrences out, we can just say, I'll just show it here, right? So before we had bab, right? Well, we're just going to add A on both sides. One C on both sides. 1D on both sides, right? 1E on both sides. And so it kind of goes infinitely, right? So we know that determining on whether or not a string is a palindrome doesn't really have anything to do with the number of even occurrences, right? Because even occurrences will always make a palindrome. But in this following example, we can see that, right? We have A, B, B, C, C, D, D, E, E, right? And this is not a palindrome, but you could easily split all these occurrences up into 1/2 on the left side, 1/2 on the right side, right? And it would be a palindrome. And so for the second example, right, if we return, we said A equals 3 and B equals 2, right? So what's interesting here, right, is that B has an even number of occurrences, right? Which means that, like we said, one letter is going to go on the left half, one letter is going to go on the right half, right? But A has an odd number of occurrences. And those of you who are more comfortable with recurrence relations will know that like an odd number is just an even number plus 1, right? And you don't even have to know recurrence relations to know that, right? So what does that mean? It means that if we have an odd number of occurrences like 3 or 5 or 9 or 7, right, you can just subtract 1 from it, right? You'll get an even number. So we have 2 here, right? So you can just place 2 divided by 2. You can place 1 on each side, one on the left side, one on the right side, and you can place the final remaining odd number in the center, right? But we know for a fact, right, with this pattern that you cannot have 2 letters with odd occurrences, right? So if we add C equals 3, let's do the same thing. You know that we can make C, we can make a proper palindrome by just subtracting 1 from C, so we'll get 2. We'll place 1 C on one side and 1 C on the other side, but then we try to place a C in the middle, and it's no longer a palindrome, right? There's just no way to make this a palindrome if we already have 1 odd occurrence. And so what we're going to start to notice, right, is that these are examples for not palindromes. We know that when we can only have, now we notice, right, that we can only have 1 letter that has an odd number of occurrences and an infinite number of other letters that have even occurrences, right? Because even occurrences always split evenly on both sides. But an odd occurrence can only split 1/2 on the other side, 1/2 on the other side, and then the one remaining letter that makes it odd will go in the center. So 2 letters can't go in the center, right? Unless they're the same. So that's why we don't have to worry about even occurrences. So here we have 3 even occurrences. 3 odd occurrences, because 1 is an odd number, right? And there's no way to rearrange A, B, C to make this a palindrome. And so we have the same thing here. We have a little bit of a different example before, except we added C here. So we have A, B, 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 and C. So 3 is an odd number of occurrences. So we can try and make this a palindrome. We'll place A on the first half, A on the other half, and then we'll place A in the center. So then we have an even number of occurrences for B. So we'll place B on the first half and B on the other half. Perfect. Now we have C remaining. Well, where do we place C? Because we can't place C in the middle, right? Because A is already in the middle. So this can't form a palindrome, right? Bacab is not a palindrome. Code suffers from the same thing, which is our first example. All of its letters have odd occurrences, therefore no letter can share the middle. Only 1 letter can go in the middle, right? And then we have Kerouac, which actually is a palindrome. Why? Because all of its letters, right, have even occurrences except for 1. So we know that the one deciding factor of whether or not a string can be rearranged from a palindrome structurally is whether or not it doesn't infringe on the 1 odd occurrences rule. So once we know that a string could be a palindrome if it only has 1 letter with an odd occurrence, right? So now we know that to be true, right? And so we can kind of template this greedy solution. So we have this. How do we check if a string only has 1 letter with odd occurrences, right? Well, we could use a data structure like a dictionary, which is just going to store a mapping of letters to occurrences. And then from there, we could just iterate over our dictionary's keys right? And then once we iterate over our dictionary's keys, what we'll do is we'll calculate, right? So count how many letters have odd occurrences, right? And if any of our letters, if we have one odd occurrence, that's great. But if we ever go over one, we know that it's impossible. We couldn't possibly have a palindrome here, right? So we'll iterate over our dictionary keys, right? If letter is odd occurrence, right, then we'll increment odd occurrences, right, which is just some variable which is going to store how many odd occurrences we've found so far, right? We're going to have another if that says if odd occurrences greater than 1, then we're just going to return false, right? And if we make it through this whole thing and we never return false, we'll return true because this palindrome can permute. So we can just do that here. So I'm just going to delete all this stuff up here. And then we're just going to say let all strings, oh no, not all strings. Let's just call it let mapping just to be really general. And this is going to be mapped as a string to a number, right? And they're just going to create a new map here. And then we're going to iterate over the strings. So we're going to say for let letter of S, right? And then we're going to say if letter is in mapping, what are we going to do? Well, we're just going to increment the occurrences, right? So mapping sub letter is going to be equal to mapping sub letter plus 1. Else, right, we haven't seen this letter in the mapping yet, right? So we should add it. And this is the first time we're seeing it, so its occurrence must be 1. And so here we're going to declare our has. So now we have this dictionary of letters to occurrences, which is great. Now we need to count how many odd occurrences we're going to have in our dictionary when we're iterating through it, right? So we're going to create odd occurrences, which is going to be a number, and we're going to set it to 0. Here we're going to actually iterate over our dictionary's keys. We're just going to say let key of mapping. And then, oops, I messed up there. And then now we just have to do what we said. We already wrote the scaffolding, and this is why it's good to write scaffolding, because it kind of helps you just make sure your logical propositions make sense. And so we're going to say if letter is odd occurrence. So how do we do that? So we have to look up the occurrences for our key here. And so this might make more sense if I change this out and I say let letter of mapping. So for our letter, right, how do we check if it's an odd occurrence? So mapping subletter is going to give us our occurrence. So now we have the number that we're working with. How do we check if it's odd? Well, typically you do mod 2 does not equal 0, right? And so that's going to check if our occurrence number is odd here. Because if we did mod 2 sub 0, mod 2, and we got 0, that would mean that that our occurrence was even, right? Because 2 went into this number and gave us no remainder. But if it's not 0, that means it must be odd, right? Because there's only the state, right, for numbers there is either odd or even. There's no in between. So we're just going to increment odd occurrences. Odd occurrences plus equal 1. Now, if odd occurrences, right, is ever greater than 1, that's no bueno, right? Because we said if a string, right, if its occurrences in a string, for a palindrome to exist, we can only have one letter, right, that can hold the middle spot. So if our middle letter is going to be C, and there are 7 occurrences of C, 3 occurrences of C will go on the left-hand side, 3 occurrences of C will go on the right-hand side, and since we have 7 occurrences, the final occurrence of C will go in the center. If we have an odd number of letters in the string, only one letter can go in the center. So only one letter can have odd occurrences, right? So we can just return false there. And so if we made it through this whole thing, right? We made it through this whole thing without returning false, then boom, we can just return true for free, right? And so we should be able to run this, and this should be good. We'll see. I might have messed up. Cannot find name mapping. I put one too many P's here, unfortunately. And so let's try our test case again. Oh man, I said let letter of mapping. That's my bad. I'm supposed to say let letter in mapping. Yikes, man. Boom, and so our test case works, and then we can just submit the whole thing. And then boom, so we're good there, right? So what is the time and what is the space complexity of this? So the time complexity of this, right, has to do with the number of characters in the string. So you could say that the time complexity is going to be linear time, right? Because where n is the number of characters in the string, so we're iterating through the strings to create a mapping of letter to occurrences. Then we iterate through our dictionary, right, to calculate the odd occurrences. In our space here, the problem solution says constant time. I'm going to be honest, I don't really understand why it's constant time. But the intuition there apparently is that our dictionary is going to be only store unique and distinct elements, right? And so in a string, since our dictionary is going to be distinct, a string, right, only has so many characters, right? So our string possibilities, right, are going to be bounded. Therefore, our dictionary will be bounded. And so I think that's why it's constant time. But I think that might also have to do with how this problem is defined with the constraints. But that is the solution to 266 palindrome permutation.